So welcome to the lecture on multi-degree of freedom system. So we have discussed about the degree of freedom. So degree of freedom of any system is the minimum number of independent coordinates that are required to express the motion of the system. And we have discussed single degree of freedom system and 2 degree of freedom system. So multi degree of freedom systems or the more than 1 degree of freedom system, they are multi degree of freedom system. However, we can easily handle the 2 degree of freedom system manually. We can write the equations and we can solve. However, when the degree of freedom increases, it is difficult to handle manually these equations, and therefore we form the matrix and we solve using the matrix laws. So here we will discuss any system, how many degree of freedom it should be expressed in. So here example is one vibration isolator. So we can see here is the spring and some damper system, and it can be idealized as a single degree of freedom system. So here is a spring and damper and this mass. So it is a single degree of freedom system. However, if we have this system, so we have this anvil is high strength steel plate, and there is some hammer that is coming from the top and it hits this anvil, and the material that is on this anvil that can be shaped. So here, and there is elastic pad to reduce the vibrations that is transmitted to the foundation, and here is the foundation block, and that could be some concrete block, and here is the soil. Now this is a real practical system, and as we have already discussed that if we model a system with less number of degree of freedoms, like single degree of freedom, so these equations are easy to solve and they give us quick insight into the problem. Although when we increase the degree of freedom, we are adding the complexity of the system, and so we are complicating the equations, we are adding more parameters. However, we are doing this to get more accurate model. So when we have more, so we can start a system to model with some low degree of freedom, maybe single degree of freedom, and then we can gradually upgrade that model to a higher degree of freedom system. For example, here we have this system and we have model is here as a single degree of freedom. So here is the mass we have considered of anvil and the foundation block. We have neglected the mass of the elastic pad here, and the soil's damping and stiffness is here taken, and so this is a single degree of freedom system. When this mass is, the hammer is hitting this anvil, what is the response of this when we have this damping and stiffness? Now we can increase the degree of freedoms by more components, adding more details. So for example, here we have introduced the damping and stiffness of the elastic pad, because elastic pad will have some stiffness and some damping, and Therefore, we have introduced this because this is between the anvil and foundation block. So, we have introduced the stiffness and damping of this. Moreover, here there is foundation, that is now another mass, and then damping of soil and stiffness of soil. So, we have modeled a system in terms of two different degree of freedom system, and from this model we can't tell very accurately that what will be the response of anvil and foundation block. We can't differentiate their responses, but here we can differentiate. We can have a response of anvil and different response of foundation, as it can be from in the practical situations. Now we have some another model. Maybe here we have some 3-story building, and this 3-story building, so this building have some columns or the walls, they work as a stiffness element, and then there are the floors, the mass where. So we can model this system like some mass stiffness system, and this stiffness is representing a spring property. So we can again model it as a K1 M1, K2 M2 and K3 M3. So a 3-story building can be modeled here as a K3, this spring and mass system of the 3 degree of freedom system. So this is the objective of studying the multi-degree of freedom system, that the more accurate models, more complex models are the multi-degree of freedom system models. Now we take a general case of a spring mass system, that is multi-degree system, and we derive the equations of motion for that system. So let's take this system. So this is a spring mass system. So here we have this K1, M1, K2, M2, K3, M3, and this is K4, and this is M n minus 1, K n K n minus 1. So this is a multi-degree of freedom spring mass system and we are interested to know how to write the equations of motion for such a system. We have n number of masses and stiffness. So here we have M1 and we can show the free body diagram. So we have a force that is K1 x1, and if we assume x2 is greater than x1, so this is pulling this spring force K2 x2 minus x1. Now we have M2. So M2 is here applied with the same force K2 x2 minus x1, but from M3 it is being pulled. So here K3 x3 minus x1, and then this M3 is being pulled here with the same force K3 x3 minus x1, and to the downside it is K4 so this is x1 double dot, this is x2, so this is x2 and this is K4, this is x3, now we have this last spring so here we will have mn kn xn minus xn minus 1. So now the free body diagrams of all the systems from M1 to Mn has been shown. Now we will apply the Newton's law to write the equations. So we will have sigma f equal to mx double dot, and so we will write this so m1 x1 double dot equal to minus k1 x1 plus so for mass m1 we have written the equations. So mx1 double dot m1 and then the forces, that is k1 x1 that is upward and k2 x2 minus x1 is in the direction of x1 double dot, so it is positive. Similarly for m2 we have this force but opposite to the direction of x2 double dot, so it is negative, and this force is in the same direction of x2 double dot, so it is positive. Now for m3 so we have this force that is opposite, so x3 minus x2 and plus k4 x4 minus x3 and so we can write for this mass Mn so mn xn double dot equal to minus kn xn minus n minus 1. So because here is the mass n minus 1, so the motion, relative motion xn minus xn minus 1 into kn. Now we have to adjust these terms. So here we can write m1 x1 double dot plus k1 x1. So here k1 x1 and then here is k2 x1. So we will have k1 plus k2. So we will have k1 plus k2 x1. And then if we take this other side, so minus k2 x2 equal to 0. Then for this m2 x2 double dot, now we have x1 k2 x1 so we have minus k1 k2 so we have minus k2 x1, so it will go other side, plus so k2 x2 and k3 x2 they will go other side, so it will be k2 plus k3 x2 and then k3 x3, so minus k3 x3 equal to 0. Similarly for this equation, so we have m3 x3 double dot now x2 term, so it is minus k3 x2 then k3 x3 and k4 x3, so we will have plus k3 plus k4 x3 and minus k4 x4 equal to 0. Then here mn xn double dot and then here minus xn minus 1 into kn and then plus kn xn equal to 0. So we have adjusted these equations. So here we can write m1 x1 double dot plus k1 plus k2 x1 minus k2 x2 equal to 0. Then m2 x2 double dot minus k2 x1 plus k2 plus k3 x2 minus k3 x3 equal to 0. We can again write this m3 x3 double dot. So I am adjusting this term. So this x1 is no here, then x2 minus k3 x2 plus k3 plus k4 x4 x3 minus k4 x4 equal to 0. And here these terms are 0 x1 and here is plus 0 x3 plus 0 x4 plus 0 x4 and so on. So and other terms are 0. Again here we can write for mn xn double dot, and so all the other terms 0 x1 0 x2 and so on, and here we have minus kn xn minus 1 and plus kn xn equal to 0. Now we have a set of n algebraic equations and we have n variables. So we have x1 and xn. So now we can this n equations we can adjust in terms of matrix. So we can write here, so we can write so m1 and then 0 0 0 so on, then 0 m2 So this m term x1 dot terms we can write in this form in a matrix. So m1 x1 double dot and this is m2 x2 double dot, this is m3 x3 double dot, and then this is mn xn double dot. Now the second terms, stiffness terms, we can write plus, so here we have k1 plus k2 and then minus k2, then 0 and then 0 and so on, then minus k2, then k2 plus k3, then minus k3, then 0, then 0 and then minus k3, then k3 plus k4 and then minus k4 and so on. So this we can write, so here so we have here kn so we have here minus kn so we have written this algebraic equations into matrix form. So if we want to get the first equation, so we have m1 x1 double dot because other terms have 0 plus k1 plus k2 x1 minus k2 x2 and other terms are 0 equal to 0. So we will get the first equation. So all these n equations we can get from only this matrix, and therefore we can write this as m x double dot plus k x equal to 0. So here m is n into n square matrix and it is known as the mass matrix. K, that is again n into n square matrix, and this is known as the stiffness matrix. So we see that how a multi-degree of freedom undamped system, the equations can be adjusted into a matrix form, and now we have these just a matrix equation can be solved, and we can solve for the response of this system, multi-degree of freedom system. So we need to use the rules of matrices, and so when we deal with multi-degree of freedom system, we need the mathematics of matrices, we need to work with matrices, and several softwares are based on these matrices. So it is easy to deal a multi-degree of freedom system in software. So now I stop here and see you in the next lecture. Thank you.